Our lesson today is how does the pH scale work? We're going to start off with just a regular glass of water, H2O. Now most of the water in a glass of water is going to stay just as H2O. But remember, water is a neutral substance, so we know its pH equals 7. And we can write water as hydrogen hydroxide, HOH. The hydrogen in water acts like an acid, and the OH in water is a base. So water has the ability to react with itself because it's both an acid and a base. Let's check that out. Let's say this water molecule here is our acid, and this water molecule here is a base. And again, that's just randomly chosen. So acids give hydrogens away. So let's say this water molecule gives its hydrogen over to this water molecule. That'll chemically change water into HCl positive, which is called the hydronium ion, and the hydroxide ion. We have experimentally determined that this process, being reversible, does create equal concentrations of ions, 10 to the minus 7 molarity for the hydronium ion, and 10 to the minus 7 molarity for the hydroxide ion. And we see our balance here is level because they're equal concentrations of both ions in solution. And that's why it's neutral. Now remember, this is a reversible reaction. This hydronium ion could give its hydrogen back to OH, remaking water. But then it goes forwards again. So it reaches an equilibrium point where we have 10 to the minus 7 molarity of both ions. Let's do our significant definitions now. pH equals the minus log of the hydronium ion concentration. There's another definition. pOH equals the minus log of the hydroxide ion solution. Let's take those logarithms down. Well, this 10 to the minus 7, the pH for that would then be 7. The exponent's 7, but we write it positive here. The pOH is also equal to 7. Okay, so then we see that 7 plus 7 equals 14, of course. So now we have another significant definition. pH plus pOH is equal to 14. And that will always be true. So what we do is we tip the scale one direction or another, causing these numbers to become different, but they must always add up to be 14. Let's see how this works. Let's tip the scale and create more hydronium ions than hydroxide ions. Let's say we have 10 to the minus 4 molarity for the hydronium ions. Let's calculate the pH for that. Well, the pH for that's going to be equal 4 because our exponent is 4, but we write it always as positive down here. Well, we know that pH plus pOH must always equal 14. So I've got 4 here. We know it must equal 14. We think, well, what number must I add? And of course, that's 10. So our pH here is going to equal 10. So if I go backwards, that'll be 10 to the minus 10 molarity. Because remember, it's positive here, but here it's negative. So let's take a look at our scales here. So this is 10 to the minus 4 molar, and this is 10 to the minus 10 molar. 10 to the minus 4 is greater than 10 to the minus 10. Now don't let your exponents get confusing. These are negative exponents, and that makes zeros go in front of the number. So this will have fewer numbers in front of the number than this one will have. Therefore, it's greater because these are negative exponents. So this is an acidic solution because we have a greater concentration of hydronium ion than we have hydroxide ions. Notice how the pH drops. The pH here is less than 7. Let's tip the scale the other direction, where we have greater amounts of hydroxide ion than we have hydronium ion. Let's make this have a 10 to the minus 9 molar hydronium ion concentration. Well, then I can take the pH of that. I know that that's going to equal 9. Because again, that's a negative exponent. We write it down here as positive. Well, we know pH plus POH equals 14. So I've got 14 here equals, I've got a 9 here. And we think, what do I need to add? Of course, it's a 5. So I now know my POH is equal to 5. I go backwards then. This makes 10 to the minus 5 molar. So let's do our scale here. 10 to the minus 9 molar for our hydronium ion concentration is definitely less than 10 to the minus 5 molar. So now we have a basic solution. In that case, pH is greater than 7. But hopefully you can understand now that when we get a pH greater than 7, we actually have less acid present. It might be a little counterintuitive. You think if the pH goes higher, that means it's a greater number. But these are negative exponents, and that's why the hydronium ion concentration gets smaller when pHs get higher. Let's practice this. Okay, we have several solutions here. Let's start off with a 10 to the minus 2 molar solution of hydronium ion. But we then know the pH of this has to be 2. If I take the minus log of that. Then I think to myself, well, I know pH plus POH must equal 14. So then I think to myself, what can I add the 2 to get 14? So that must be 12. So then my concentration is 10 to the minus 12 molar. My pH is less than 7. This must be an acidic solution. What if I start out with something given like this? I'm given a POH of 5. Well, then I need to think to myself, let's go backwards. I know 5 plus a number must always equal 14. Well, let's put that here in the proper place here. The POH would be there. Okay. So then we know that the pH must equal 9. Okay, and the OH concentration then would be 10 to the minus 5. Okay, and the hydronium ion concentration would be 10 to the minus 9. And again, those are molarities. Okay, since my pH is greater than 7, I know this is a basic solution. Okay, so it's pretty easy to do. Now, last but not least, let's say I do have a POH of 7. Well, we know that that's our neutral solution because pH must be 7. And these must be 10 to the minus 7 molar. And this must be 10 to the minus 7 molar. Therefore, neutral. So it's as easy as that. Pretty easy equilibrium. But again, our driving equation really is pH plus POH equals 14.